I think we can get started. Um, just to get a quick poll, who was not at the previous MM Mondays? There was a couple, yeah. All right, cool. So we got some new people. Nice. In case it weren't obvious by what I just said, this is ML Mondays. So this is week 3. We're going to be discussing something called computer vision. So before I go any further, obligatory plug. This is if you're interested in Hack AI, which is going to be a cool AI-related hackathon in about a month and a half, mid-April. Use the QR code to sign up. If you don't get the chance to look at this yet, I'll go back to it at the end of the presentation, and it's on the Discord or most AIS things because it's a really cool event that we're trying to get more people involved in. But I will skip ahead because I know you all are interested in what we're here to talk about. So today, as I've already mentioned, is computer vision. You can see that we have a few other topics going in. Week 8 is still TBD. So that week's basically going to be meant for if anyone has a particular topic that they really want to go into more in depth, or maybe try something more interesting. If you are interested in something like that, please let me know. Probably near the end of the presentation, and I can make a mental note, and we'll maybe do that in week 8. So today, it's our agenda. It's not going to be super detailed, but basically, what's computer vision in a nutshell, and a few of the simpler topics within computer vision, like image classification and object detection. And we're going to do a cool workshop. So to actually start this presentation, what is computer vision? Quick poll: who here has never heard of computer vision before looking at tonight's presentation? Okay, looks like everyone's heard of it. It's pretty simple. It's basically just AI that derives something meaningful from visual images. So, for instance, image classification, object detection, object tracking, which is what's shown in the bottom right, which is pretty cool. And there are a lot of things you can do with image data. As you could probably guess, but computer vision is the section of AI that is specifically focused on that. So we'll start with image classification. And if anyone has seen image classification before, they might have seen this image before. Given an image and a set of classes, determine what a class is. In this case, for each box, you've got to determine if it's a chihuahua or a muffin. Now, for a computer, this is actually a pretty difficult task because they look pretty similar. But it is the whole idea that it's illustrating. It might not be so for a human. We've had such a long time to figure out how to really discern different things. But for a computer, they can only look at things at the lowest level, and it is much harder of a task for them. So this would be trivial for us. But for a computer, this might take a lot of time and might not be simple. Oh, yes.
So would that be a high complicated task for a computer to do, high-level computer vision?
So this would be a type of image classification. This particular data set would be a fairly hard one because it's set up in a certain. This is just one that is not clearly obvious. Like if I had cat and dog, it'd be a bit easier, but I chose a specifically hard one to illustrate that. The way you'd approach it would still be the same, but it might not be nearly as effective as other options. Does anyone else have any questions before we proceed forward? Just to verify, if anyone does have questions, feel free to raise your hand anytime during the presentation. I will answer any questions you have. This is meant to be a learning experience, and so you shouldn't feel bad about having a question because that's the point of this. So before we go any further, I'm going to go briefly over a couple things from last week. So basically, going up to the next slide real quick, there's a concept in machine learning called a neural network. Basically, you have a bunch of nodes with different layers that eventually get you an output, which is going to be what your output classification is. So you'll see all these connections between each of the layers. This is a deep one because there's a lot of layers involved, but this is something that's going to be used a lot in most machine learning applications. So if you're confused on what this is, basically every node is similar to something called a perceptron. Basically, like a neural net, basically you are given a bunch of inputs So they can be something, for our case today, it's going to be a lot related to pixel values. So for instance, this could be 0 to indicate that a certain pixel is black, for instance, or I forget which one it is. But basically, you can feed in a bunch of information. You can do a weighted sum. So you can do, they can all have different weights associated with them to get a certain sum. And then you apply a function to it that is usually determined during design. I'm not going to go too in-depth with these, but generally we're going to be looking more into some activation functions called ReLU and softmax. You don't even necessarily know what they are, but if you are curious, do a Google search and you will see the function. It is not too difficult to see, but it's important for implementation purposes. Does anyone have any questions on what a perceptron is? All right. And yeah, this is basically if you connected a bunch of perceptrons together. The process for actually having a machine learn on this is something I won't really go into in depth, but basically there's a concept called batch propagation that allows basically a neural net to kind of go back to the mesh and adjust weights in order to improve its accuracy for the future. If you are interested in that, look it up, it's really cool. But I won't go over that because it's a bit too math heavy for an intro level thing. So now that we've done that, let's look into something a bit more specific to computer vision. So there's a special type of neural network called a convolutional neural network, which has convolution in it. That's the whole idea. Basically just have a special type of layer in it called a convolutional layer, which I'll be getting into later if you're confused. But they're nice because they are very good at taking like multiple dimensions of data. Like if you imagine a 2D or 3D image, 3D image would be kind of weird, but a 2D image, and you can basically figure out patterns spatially, like see that you have like a diamond shape or like a certain angle in a certain place. That type of layer is particularly good at detecting that, and thus they're really nice for our type of application. But to know what a convolutional layer is, you have to know what convolution is, because not everyone's heard of that. That is just a mathematical operation to find patterns in a filter in a matrix. So imagine that this is our input. The values themselves aren't this important. It's mainly just to demonstrate the idea of convolution. But imagine that you're given, like 1 would be, let's say 1 is a black pixel, 0 is a white pixel. So you have a certain shape. You also have a couple filters, which are basically smaller matrices that have some kind of pattern that we're trying to look for. So in that case, it's just a diagonal line going from top left to bottom right, and there's a different filter for filter 2, and so on and so forth. You tend to have a lot of filters in convolutional neural networks. They're the things that basically describe the patterns we're looking for. So to actually do this, in this case, the filter is 3 by 3. So we just go apply this matrix as we go to every 3 by 3 block in this image. So we start here. We do something called the dot product. Does anyone not know what a dot product is? Okay, so what a dot product is, basically, it's pretty simple. It's just if you were to multiply the first value by the first value there, the first value would be 1. You can multiply 0 by -1, you get 0. And you go so on and so forth with the whole matrix, and you just sum the results. So in this case, this first block, if you do the dot product with the filter, you will get 3. And you will just continue to push this kind of this view. You will push this red box further and further across this thing until you've gone over everywhere. And you'll end up with a smaller matrix that has basically higher values are going to indicate a stronger match with our filter. So we have 3. That's a very strong match for our filter. Just out of curiosity, why might I want to have negative values in areas that I don't have this diagonal line? Okay. If no one knows, that is fine. But the way that works, think about it for a minute. Let's just say I were to have some kind of box where it was all 1s. If it were all 1s, and the filter over here just had 1 0 0 0 1 0 0 0 1, then you're going to get a huge value every time because it's like the maximum possible value. You're going to get like 3 in any case, and that's not really that informative as a filter. So you have the -1 there to indicate. Let's just say I were to do the same thing. I had a box with just 1s in it. With the -1s in there, if something doesn't follow a pattern, it will penalize it. And because of that, you will end up with things like -1, indicating that they don't follow a pattern, the pattern that we're looking for, and thus we don't care about them for now. So if we were to continue this, we would end up with a matrix that looks like this, a 4x4 in this case. And you'll see that there are the top left and the bottom left corners seem to have the highest values and are the closest matches in terms of our pattern finding. Does anyone have any question about this? I understand it's a bit. Yes?
How do you get those values? The 3 and 3?
These ones? Like this 3 and this 3 specifically? So I can go over I have a better visual example for the first one, so I'm going to go over that first. This 3, you basically gain by doing what's called the dot product, as I mentioned, between these 9 values and those 9 values. And if you were to do the math, it's pretty simple in this case. You're just multiplying like 1s and -1s and 0s. You will end up with 3. You'll see, just looking at it intuitively, it's the exact same pattern here. It's a perfect match. So this is also going to be a 3 for this. Does that answer your question? Yeah. All right, cool. Does anyone else have any questions about convolution? Yes.
How do you come up with the filter?
So that is an interesting question. In most actual modern implementations of convolutional neural networks, the filters are kind of learned and figured out in the background. Because you might end up randomizing at the beginning and end up with a bunch of patterns that we're not actually really looking for. As we learn what to look for, eventually we'll figure out what patterns to look for. And by we, I mean the neural net. And this filter will change. We don't tend to specify these filters ourselves. It's done in the background. If you're curious about that, I would definitely look into it, but it isn't something that's necessary for this. But it is a good question. Are there any other questions about convolution? All right, I'll keep going. So once we have this convolution, we have this nicer matrix. We can basically make that matrix a bit smaller and easier to work with. So let's just think about this for a minute. Imagine we have the same matrix we just came up with before, 2, 3, 0, 1, blah, 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 so on and so forth. Actually, I don't know if it's the same matrix or not, but I've made a new one. It works. And we can basically determine whether a pattern is in a certain space. We can reduce that matrix to about we don't have to do everything. So let's look at this 2 by 2 right here. It has 0, 1, -2, -2. Not really any strong matches there. The strongest match is a 1. And for the purposes of trying to see if there is a pattern in a certain space, that's all we need. So we can just take the maximum value of this box, put it right there. So we can reduce matrices to a smaller size, which are easier to work with, and tend to be a bit more, a bit cleaner, less overfitting, and it's just nice in general. But yeah, flattening layer is pretty self-evident. You take a 2D thing and you make it 1D, or make it more than 3D. Do you have a question? Okay, I wasn't. Okay. But yeah, this is pretty straightforward. 2D to 1D. As you'll see, most layers that we work with don't tend to like multi-dimensional stuff. That's really what a convolutional layer is for. So we try to convert it from 2D to 1D once we're done with our image stuff. Yes?
Is the 1D one vertical?
Not necessarily. I guess it's kind of arbitrary in our case. If it's 1D, it doesn't really matter. I could make it horizontal and it won't make any actual difference because it's one-dimensional. If it was 2D, it'd be a bit different, but that's just what worked out in this visual. Any other questions from this point? So no? All right. Layer I'm going to go over next. Dropout layer is a bit of a misnomer because it isn't actually really a layer. It's more of something you apply to an existing layer. So what a dropout layer does, you'll see that this is like a pretty normal neural network. There are a lot of connections. Like actually every single node in this layer has connections in every node in this layer. That's a lot of connections, especially when you have neural nets with like 100 plus perceptrons or neurons, what they generally call them, per layer. You'll end up with a crazy number of connections, which is a lot to work with. It's a bit messy. Dropout is nice because we choose to remove a random percentage of those connections. So for instance, you see over here, we remove a bunch of the connections, and we do it this way. So basically, we reduce some overfitting a bit. So if we were to keep track of every little thing, then there might be something coincidental in our test data, or in like our training data when we're working on something. Like, let's just say that somehow in our training data, every single in every single case where there's a Chihuahua, for instance, the Chihuahua muffin example, every single case there is a green pixel in the bottom left corner. Now it's going to think that every single object, every single image that's ever going to get with a green pixel in the corner is going to be a Chihuahua when we know that's not the case. In a way to potentially prevent that type of thing, we're going to remove kind of arbitrary things from our layer, so it's less likely that stuff like that will happen. Any questions about dropout? All right. I guess that'll be that'll be it for CNNs for now. I'm going to briefly pivot into a new area, object detection, which, as you can see, is pretty nice. You can see in this particular example that you can actually like figure out not only what something is, but where it is in the image, which is useful, as you can imagine, quite useful. There's a few different algorithms for this, but the one that's probably the best right now is an algorithm called YOLO. You only look once. It's called that because unlike other similar algorithms, you don't look over the same image multiple times. You just look at it once. It's a pretty fast and accurate algorithm, so it's gained some popularity because, as you could probably guess for someone like this, you want something fast. If you have a huge image, you have many images. If you've ever done any kind of machine learning training on something that's more complicated than the most basic examples, you don't like things that are slow. It's just not great. So having something fast is great. But how does YOLO work? I'm going to go over this at a really high level because it's actually a relatively complicated algorithm. I'll provide some better resources later in the slides if you are generally interested. But we do a few things with YOLO. First, we basically make a huge grid on our image. They're called residual blocks in the algorithm. But you'll see that there's a bunch of blocks. And in each individual block, we determine if there's an object in it. We have some other neural network that kind of basically sees, hey, there's a person in this block right here. Maybe that's important. You see, oh, there's nothing of significant importance in this block, so we won't do anything with it. And so we just apply residual blocks. Then from there, we use the grids to make bounding boxes. So if we go back to this previous image, you'll see that there's, like right here, for instance, there's for this person, there's basically a bunch of residual boxes together. A bounding box would just be a bigger rectangle that covers everything. Another thing that this algorithm does is something called intersection over union, IOU. But basically, without getting too deep into it, it's basically just a way of seeing whether we're given some test data where it's actually labeled for us, and then our predicted algorithm. This is basically a way of measuring how close we are to our actual answer, because we can't just like see, oh yeah, this rectangle is different size than the other one, so it must be wrong. We need something better than that. So basically, we just take an area of the overlap versus divided by the area of the union. If you have a high IOU, that's very good, because then basically you have an exact match. Because if the area of overlap is the same as the area of the union, the same box, it's fine. It's great. It's never that easy, but when it is, it's great. And then just briefly, the residual blocks, when they actually use their object detection, they use a deep CNN model, kind of like what we described before. They have a specific one that's a bit more complex. but they use CNNs are used in a lot of different areas in computer vision. So this is just another way of going at it. If you are genuinely more interested in this, there is a pretty nice tutorial for making like custom YOLO detector at this QR code. As a reminder, these slides will be available after the presentation in case you don't see this. But it is a pretty interesting thing if you are a bit more experienced in coding. If you're not, I'd probably recommend staying away from this for now, just because it is a bit of a messy collab document, but it is cool if you're able to get through it. Does anyone have any questions or comments about YOLO? I understand that was a bit more complex than the image classification. This is mainly just to show that there are some other options out there that are pretty interesting, but things do get more complicated outside of the basics. So, at this point, anyone who is able, I appreciate it if they could use that QR code and get onto the computer with our collab document. I can give you the link. Hang on. That's a bit messy. I'm going to make something easier for you guys. Hang on. That might also work. Does anyone not have access to a QR code reader or the AIS Discord? You do? No, I'll put it in there. I just wanted to make sure that there wasn't an. Where would be a good spot for this? Okay, let's just put it in general because I'm a rebel like that. Okay, if you don't have access to your QR code reader, this should also work. Please let me know if there are. Is there anyone that wants to that doesn't have access to this workshop as of right now? All right, then we'll continue. So, does everyone see something similar to this? Does anyone not see this if they are following along with this workshop? Okay, because there was a bit of an issue last week. I just want to make sure everyone sees this. So, before we actually start on this, I would, because you can't actually edit this one, I'm going to need you to save a copy of this workshop in the drive using File, Save a Copy in Drive, and then just follow that one instead. That one you're going to be able to edit, which is kind of important for this workshop. But there's that. What I will also want you to do is go to Runtime, change Runtime type, and then make sure that it's on GPU. Yes? You good? Okay. You're going to want to switch to a GPU hardware accelerator. That'll make the training step a bit faster. GPUs are generally pretty good at machine learning. There's a reason that so many people like them. Yeah, I would highly advise that, or the training is going to take considerably longer than you'd want. Did anyone have any issues with that part? Yes? You need what? Get to where specifically? The GPU thing? Okay, so follow what I'm doing up here. Go to Runtime, change Runtime type, and then I think for you guys it might still say none, but if you click on Hardware Accelerator, you can choose GPU. Does that answer the question? All right, then we'll continue. So you can choose to manually connect, but also if you run something, it'll automatically connect. So that's a bit arbitrary. But we can actually start a workshop now. That's great. So before we do anything, we need to import a bunch of stuff. These are some nice Python libraries that we can use to make our lives a lot easier so we don't have to code neural networks from scratch. That would really suck. But yeah, just feel free to run this. This will take a little bit because there's a decent number of modules, but that's one of the benefits of Python. You get access to a lot of cool stuff. So basically, for this particular workshop, we're going to be going over a data set called Fashion NNIST. So if you're interested, there's a link. But the way this data set works, it's kind of like a data set you would use to test, make sure that a certain model makes sense, that it works. But For this one, there are a bunch of images. They are 28 by 28 pixel images, which are all of basically they all, okay, I'm not seeing a good visual here, so I'll just show you what I have on. You'll get images probably with a different coloration because we do some modification to get to this point. But you will have images with 10 different classes. The classes are all related to fashion-related stuff. So there's t-shirts, trousers, dress, coat, a lot of options. There's 10 classes to work with. Obviously, we want to make sure that we make our model that works well and predicts these. But that's basically what our model is. This is a pretty simple case because we have pretty small images. You don't have to worry as much about speed. This isn't a particularly hard one. But when you get the chance, I've already set this up so that you guys can easily download this. So when you get the chance, just continue to run these two modules. Oh, it's because I have, hang on, let me just cancel this. All right. Basically, I already set up so that it'll save these files. And you can run train.head to kind of see what the train file looks like in a spreadsheet format. So unlike a lot of image data sets, this one's pretty nice in that it just gives you a bunch of pixels. It doesn't give you full images in the data set itself, or you have to do considerably more processing. But you'll see that there are a bunch of pixels. So they'll have a label. Each picture has a label, and there are a bunch of values for each pixel. It is grayscale for this case, so zeros are, I think they're white, and then black is 1, or something along that line. It'll be more clear in a minute, but that's not super important. So to work with the machine learning library that we want to work with, which is Keras, it's a great machine learning library if you want to look further into it. We have to basically change these from integers to floats. We also need to normalize our pixel data. So basically, we're both splitting up our data into just the image data and a label. So that way, it's easier to feed into our actual result. Because we're going to want to give the image data and not the image and the label, because that'd be like giving the answer to the thing you're going to ask a question to. That'd be weird. That's why we have an X and a Y for both training and testing. Yes? What's the error say? Do you mind if I look? That's probably because we get from this. So just to give you an idea, for this particular notebook, and also most notebooks, you need to have it where you need to make sure train and test are defined before you go over to X train and Y train. So you want to run this before you run this. That should, what? You don't have to undo it. You can just run it. You don't have to undo anything. You can technically run these in any order, though it's going to crash and do it in a lot of orders. So if you were just hit play on this one and then play on this one, you should be fine. Did that work for you? Okay. Does anyone else have any questions about what we've done so far? All right, that's a no. Cool. We'll go for this and then go for the interesting stuff. So we need to split our data a bit. So to give you an idea, there's our training data and our test data. The training data is basically this huge collection of data where we have our model actually learn something. We also have test data, which is data that our model doesn't use to learn. It is just something we use at the end to evaluate if our model works well. We do have a third class also called validation data. It seems pretty similar to test data, but basically it is kind of like if you apply test data to every, you do a bit of training and then see how it's doing. Do a bit of training and see how it's doing. Validate it's similar to test, but it basically gives you an idea as to how well your model is doing as it's training and not just at the end. But yeah, just for the purposes of this workshop, just hit play on the modules and as we go. Once we'll get to a point where you guys will have to do some actual coding, but this part won't be it's just going to be kind of running to see what this is like. So Now that we've mostly processed our data, I set up some code here to actually see what we're working with. Because for a image data, that's kind of nice. So if I were to run this, it would, one of our libraries is going to take 36 of our training samples and give them and their true labels, and they'll put it down. So you can see, let me zoom this up a little bit. I think I have this. Yeah. So for instance, this is bag, ankle boot, and so on and so forth. It gives you, it's nice to know something you're working with, because when you go through your test results and you see, oh, our model is predicting wrong in this class, maybe now you have something to work with. You know that it might be predicting it wrong because this is a particularly tough example that looks kind of like that, but it isn't one, for instance. But it's nice to know, it's a pretty bad idea to just apply random things willy-nilly to a data set you don't know. That's not great, not ideal. Moving on. Oh, and then one last thing, we have to reshape our data a bit so that it works well with our, it plays nice with some of our other library stuff down the line. We have to reshape our image data into three dimensions, which is a little weird because you'd think it'd be 2D. But there are three things. There are rows, which is obvious, columns, which is obvious, and you also have a 1 in there, which might be a little weird. What that is just, it's basically a color channel. Because we're doing grayscale, it's just going to be 1 in our case. But if we were doing like RGB images, for instance, that would be 3. Because you basically have, in that case, you kind of have 3 images kind of like stacked on each other, one of them in red scale, one in green scale, and one in blue scale. But in our case, we're just using gray because it's going to be simpler. So now for the actual fun part. We are going to build a CNN model. And by we, I mean you. But basically, to give you guys a quick overview of how to actually make a CNN model, I have a bit of example down here. But basically, we're going to be using something in Keras called sequential, which is pretty simple. It's basically just a function that makes a nice neural network for you, provided you give, basically you give each layer in a list. It's a bit cleaner. There's like some weird models on the line that might have like weird diagonal things, or you'll have stuff that feeds back in old layers. This is like the simple case where that is not, it's nothing. Sequential is pretty simple and it's nice to use. So in a typical CNN model, we'll have something like this. So first, we'll have a pair or pairs of convolution layers and max pooling layers. I have a bit of a visual down here. That way you can basically extract any patterns you have. If you have multiple convolution layers, you can sometimes have it where you have like larger scale patterns. Like instead of looking for an edge somewhere, for instance, in an image, you can like look for what might look like a beak or something. Like if you're trying to basically combine multiple smaller patterns into a bigger one. That's part of the benefit of something like deep learning as opposed to just having one layer. Then you have a flattening layer, so you can actually have any of your other layers work. You include a small number of dense layers to do some further learning on the fact that certain patterns exist in certain ways. And then you include one more dense layer at the back with the number of output classes we want. So because there are 10 different possible image classes in our case, we're going to want 10 basically neurons, I guess, in the back. So that way we can basically, the output is going to be something along the lines of 0.8. And basically what that's going to be like, to interpret that, the 0.2 would indicate that class 2, it thinks there's a 20% chance it's class 2. And like for class 9, it thinks that there's an 80% of being class 9. To be simple about it, you generally just take the highest value out of that and go with that prediction. But there's sometimes weird cases where you don't want to do that. But that's why you have 10 outputs instead of just 1, because it's binary basically. Throughout this, we might also include dropout layers to reduce basically overfitting, but that doesn't have the nice visual component to it, and that's a bit more inconsistent. So be that as you will. It is more of an art than a science to do this. Figuring out the right intuition for the right model isn't simple. It just takes some experience. It varies a lot by whatever model, whatever data you're actually working with. if it was super easy, this would all be done already, and we wouldn't have people in machine learning that earn a ton of money every year. So I put down a kind of a reasonable starting base for you guys to start with. So for instance, in my starting case, I have a convolutional layer. It's 2D because we're working with 2D data. We have 32 different filters that we mess with. The kernel size, which is basically the dimensions of the filter. So in the example I did before, you would have, because the filter is free by free, the kernel size is free. Yes? It's just another term for it's not super important. It's just another term for kind of like the size of a filter and things like that. I might not be 100% on that, but it's not that important for this case. There's an activation function, ReLU. I think that might just be the default. Don't worry about it. And for this first layer, we are going to need an input shape or image, which in our case is image shape. That way our model knows what kind of data it's going to take in. It can't just take in arbitrary things. We have to define what it looks like. Then we have a max pooling layer, which in our case, it's a pool size of 2, which is kind of like this example. We pooled basically 4x4 into a 2x2. We're pooling 2x2 boxes. There's a dropout layer, flatten layer, and then some dense layers. That's the general format you use. You could maybe experiment with this by changing the number of filters, changing the kernel size. You could basically change it, when the dropouts are bigger, you could add more dense layers, another set of convolution layers. There's a lot you can mess with. As I said before, there's a lot you can do. But you can basically put your layer here. If you want to be really lazy, you can just use mine. But also, if you want to actually experiment with it, you can kind of mess with this. And yeah. So I'm going to continue for a bit to kind of show you what to expect, but please start working on that now because it'll be nice to kind of see how it compares to the baseline. So once you've done that, you guys can continue doing what you were doing because it depends on each person and how you want to do it. We have to compile our model. I'm just going to quickly add something to just use mine instead of the CNN model. So I'll just have CNN model equals example CNN model. Because I am lazy, don't be me. Actually, I made this, so it's fine. So I'll just run a few things real quick. So I have a CNN model. That's good. We have to basically compile our model. So it just adds a few settings to our model that relate to actually training it. Loss is basically just a function that's used to, it's used by the machine learning a process to actually determine how well it's doing. And the metrics could be more of a human interpretable way of seeing that. There's also an optimizer which affects something called learning rate, which isn't super important, but it is important, but for our purposes, we can ignore that for now. We can just go with our defaults. Now for the fun part, we have a compiled model. It's nice. We can train it. Again, for our purposes, you can kind of leave this as is, but if you're curious, Keras has a nice documentation for all other stuff. You can change something called hyperparameterization. Basically is really nice for messing with how exactly your data trains, because that matters a lot, but that's a bit out of our scope, so we're going to ignore that for now. But this is where you're going to see the benefits of GPU. If I didn't have a GPU, this would take maybe 8 times longer. But because I'm not doing a GPU, this will probably take a minute at most, because it's going through all these things really fast. To give you an idea, an epoch is basically, in our case, let me just make sure that I got this correct. It goes over a pretty large chunk of our data and then learns it all. Basically learns given what it's seen. So when you have a bunch of epochs, it's gone over its data quite a bit. Still working on this, but it's almost done. It generally takes much longer than this. This is why we use GPUs. It's great. If you haven't done that, it's going to take at least 10 minutes to do it. Probably longer. Yes? What error do you get?
It says like internal error, graph attribution error.
You mind if I look? Okay, so there's your issue. Your model doesn't have anything.
Oh, so
So yeah, if you want to start out, you just not using it, then you modify it. Yes? Okay, so the issue here is that there are no layers. So you need to add layers. If you wanted to start simple, you can just use what I did. But if you don't, I would start off with what I have and then add something there. But this is going to be the part where you actually do need to add your own layers to this. And if you do it correctly, you should get something like what I just got. You'll see there is, for each epoch, it has a certain accuracy, certain loss, validation accuracy, which is basically what it's, on the right is what it's working on our validation data to see how well it's doing. And the training accuracy is a bit weird because it tends to be, it's like learning that same thing over and over again. So naturally it's going to do better and better. If I spend enough time on this, it'd probably get 100% accuracy, but that's not what you want. Because if your training data is 100% accurate, it's, imagine as though you were taking, you were tasked with taking some test, and then you take the exact same test, verbatim, word for word, 100 times. Of course you're going to do well later on. You can just remember the answers. That doesn't mean you actually know the material. This is why we have separate tests from what you learn. So that way it actually learns things and doesn't just memorize. That's kind of the idea of overfitting. But going for here, once training is complete, we can plot our accuracies and get a better idea of how we learned. You'll see that our loss is going down, which is good. And training accuracy is going up, which is also good. You'll see that there are two lines for each of these, a loss and a validation loss, or accuracy and validation accuracy. Generally speaking, this is great, but if I were to spend more and more time on this, the regular accuracy would get really high, up to like 1, but validation accuracy would start to dip. Again, this is overfitting. We want to make sure that validation accuracy is maximized. So this is why we kind of look at a graph and get a sense of how we're actually learning. We can also kind of see how our new model predicts our data. This is like a fancier way of looking at it. This is basically seeing for each individual class, like for the t-shirt class, for instance, how well it does in predicting that specific class. So you can see that it's not quite balanced for everything. There's like a 90% overall accuracy, but it's much better at certain ones than others. So it's important to note that type of thing because it helps, if nothing else, gives you an understanding of where your faults are in a model and how you can potentially improve it. If you want a more visual result of that, which is a visual version of that, which most prefer, is you can use something like this. You can go through like 25 of our images, get the predicted results and our actual results. So you'll see for most of these, it's correct, but you'll occasionally see something like this, like the prediction class is shirt, but it's actually a pullover. So it's not perfect. And then does the same thing here. Sometimes it's going to mess up. If I gave it more time to train, if I gave it better options for training, it could maybe do better. As a general note, if you get 100% accuracy, there's probably something wrong because that's really hard. And there's probably some problem somewhere that you're misinterpreting. 100% is very rare, especially on actually hard tasks. So just something to learn. But you'll see a bunch of options for your prediction thing. And that's our workshop. So in my model, I ended up getting something like 90%. Out of curiosity let me check. It was like 88.6%. Was anyone able to get a model that worked differently than this? I didn't get what you said. Oh, like you're increasing the number of epochs? Yeah, that can work. As I said, it can work to train long enough, as I said before, if you get to the point where validation accuracy starts to dip or validation loss starts to increase, then you've gone too far. But some training is definitely beneficial here. I just made it faster for the purposes of this presentation. That's a good call. You had your hand up as well. You changed the number of what? Okay. All right. I guess out of curiosity, how did it do? Yeah, no, that's good. That's why we mess with our architectures and see what works best. As I said, it's more of an art than a science, so you kind of have to mess with things until they work. But over time, you will gain some level of intuition for what tends to work better. For instance, you tend not to have generally simpler is better. I've had that mistake in the past where I've made like 20 convolution layers, kind of back to back. That is too many. That is way too many layers. When you get to that point, it starts to overfit or lose information that's actually relevant. And it's unnecessary. You generally don't need more than like 2 or 3. Though, as I said, it's application dependent, so you all have to experiment. Does anyone have any questions, comments, concerns, or anything related to this workshop? Yes? Which graph? This one?
Yeah. The validation accuracy just testing against
Right. It's testing against the validation set, which we are not using for training. We do it that way, so it's not. It's like a more true prediction of how well it's doing. Training is just something that's always regular. Actually, it's just always going to increase. If it doesn't, something is really weird with the program. But validation is the important part. Does anyone else have any questions, comments, concerns, or anything related to this workshop or this presentation? Yes.
How do you go about deciding how many epochs to train?
So that is a largely, you use a technique called guess and check. But you kind of just have to mess with it. See, it's partially a matter of how much time you have. Because obviously I could put 1 million epochs, and that would take forever, even if it did happen to work well. But
that wouldn't necessarily make it better.
No, it wouldn't, because as we've said before, overfitting. But this is why you'd use the graphs. If you wanted to check, for instance, you could if you have some other data set, you could set to something like 10 epochs and see if the validation accuracy is still on the upward swing and it's not going down. Then you can increase the number of epochs because there's clearly still room for improvement.
So the only factor in increasing the epochs is
I mean, there's that. It's also, you want to get to the point where you're at highest accuracy as possible. You don't want to cut it off too early or you're not going to learn as much as you could. Like if I were to cut this off at say 5 epochs, there's obviously a lot of room for improvement there. There is a bit more to it I haven't gone into this presentation, but overfitting is the simplest thing I can go over. Does that answer your question? Does anyone else have any questions, comments, or anything else? 3, 2. All right, then I guess that'll be it for tonight. So, did you have your?
you could go into webcams.
So I guess, are you asking how you would incorporate webcam data into something like this? So
just use the YOLO one. So YOLO is in it.
So I guess that's more of an issue of, okay, so there's a couple things there. So it's a question of what you want to use the data for as well. So for instance, if you want to do something as much as object tracking, you need to figure out how to basically integrate video data or basically look at multiple frames at the same time to get a sense of motion. If you wanted to just get camera stuff for something like object detection, like what I showed in YOLO, then it depends. You basically have to, that's more of an implementation thing. That depends on the camera, depends on a lot of stuff. You're kind of just gonna have to look up stuff.
OpenCV library.
OpenCV is nice. I would recommend looking at that.
Wait, so YOLO is CNN, right?
YOLO uses a CNN, but there's more to it. At the bottom of a lot of these things is a CNN or something similar. CNN is just kind of the building block for something that's really nice. That's part of why I went over it today. But does that answer your question at least to some extent? Okay. Anything else? All right. Then I'm just going to casually put this back up real quick in case anyone wants to sign up. I don't know. I'm just doing this because it's cool, and more signups is nice. But other than that, that's it. Yes. Yes, I'm going to be sharing it later. I also have the previous 2 weeks' presentations already on the Discord if you want to look for it. It should be under the resources tab. Or you could look at the presentation as well, but I imagine you can go for the slides also if you want to go over something faster.
Can you go back to the schedule slide?
Yeah, sure. So this is our schedule. Next week is going to be reinforcement learning, which is a personal favorite of mine. That's like if you want to, for instance, one of the applications of that is you can train a bot how to play like an Atari game, for instance. That's the type of machine learning it is. I personally think it's really cool. But that's next week.
Week 5, will we do like the Hugging Face lab?
Most likely. I'll have to look into it. Hugging Face is probably the best option. I think there's someone else on the team that might take over for me on that one because they are particularly interested in Hugging Face. So we'll see what happens. But yes, you should expect that. All right. I'm going to. Yes.
Can you get more data sets like this? Like the last one you got the dynamic data set, this one you got the fashion MIST.
There is a great website called Kaggle.
Okay.
This is where a ton of data sets are. This is a more simple one, but you can find data sets for a lot of things. There's even competitions for different data sets. If you're looking for data, this is the first space out. There's a lot there, and you can find a lot of what you need. Yes.
For week 8, you're open to suggestions on the topic.
Hang on, I realize I need to end this real quick.